In this video, we will describe transition state theory, which essentially describes how we get the K value, or the rate constant, for our chemical reactions. Now, you might have been wondering where the rate constant K actually comes from. Well, we can use a theory called collisional theory, which describes how reactions occur. It's an extension on kinetic molecular theory that we used for gases in the last chapter, particularly when talking about PV equals nRT. Just as a reminder, the kinetic molecular theory said that gases can be thought of as small hard spheres bouncing around in three-dimensional space undergoing elastic collisions. So we're going to assume that in order for a reaction to occur, the reactant molecules must come together and collide. So reactions cannot occur across a large distance. They need to collide in the correct orientation for the reaction to occur. They need to collide in the correct orientation for perhaps a transfer of electrons or an atom to transfer across for that to occur. They need to collide with sufficient energy, which we will be calling the activation energy, for the reaction to occur. We will be looking at diagrams like this, which is called a potential energy surface, which is a diagram indicating the relative amounts of energy of where the reactants are and then where the products are. So in this case, the reactants have more energy than the products, and so this would be called an exothermic reaction. A reaction that starts with more energy goes down to a lower state of energy, and so it must release some of that energy. Now, from some of the assumptions in collisional theory, we can obtain our equation of how our rate constant K is actually a function of temperature. So KT, or K of T, is equal to this rho, which is essentially the probability that a collision will occur in the correct orientation, times Z, which is the frequency of those collisions, E, which is just our mathematical E, raised to the negative of the quantity, the activation energy, which essentially is the minimum amount of energy needed for the reaction to occur. R is our ideal gas constant. For this one, because the EA is the activation energy, we need to make sure that our R value has units of energy. So we'll be using the 8.314 joules per mole Kelvin. A thing to be aware of, however, is that often these activation energies are expressed in kilojoules. So you'll need to do some form of unit conversion to make sure that either your R is converted into kilojoules or your activation energy is converted into joules so that your units will cancel out. And then T, capital T, is temperature. Now the activation energy on our potential energy diagram is the difference between the energy of the reactant and the top of what we will call the reaction barrier. This is the amount of energy that it takes to break all the bonds in our reaction. So if a particular atom is being transferred, this is the amount of energy that it takes to rearrange our molecules to allow for that atom to come away from its molecule. So the activation energy is essentially the height of the potential energy surface, and this is what dictates how fast reactions are going to occur. The higher the barrier, the slower the reactions will occur. So we also have what we're going to call transition state theory, which is an extension of collisional theory. So collisional theory essentially said in order for a reaction to occur, the molecules must come together, collide in the correct orientation and with sufficient energy. Transition state theory adds to this, saying when a successful collision occurs, prior to the formation of products, the reactants will form a temporary, unstable intermediate that we will call the transition state or the activated complex. You'll see it in either one of these two forms, transition state or activated complex. They're used interchangeably. It depends on where you're looking for which one you will see. So if we have a reaction, this is methyl iodide plus the hydroxy ion, or the hydroxide ion. This undergoes what, when you take organic chemistry, you'll know as an SN2 reaction, in which the hydroxide ion comes in and it will displace the iodide, right? Resulting in a product of methanol and iodide ion. The transition state is a halfway point between the form of the reactants, which would be the iodine bound to a CH3 group, and the products, which is the OH bound to the CH3 group. So in order for a reaction to occur, the two components need to collide together and then rearrange themselves in an intermediate state that looks halfway between what your reactants do and your products do. And that intermediate state we will call the transition state.